ठीक है. So now this is what we studied. Enthalpy changes basically you need to break the old bonds. They need to be broken. So just a quick recap that all the bonds that you have in your reactants, they have to be, you need to break them, preferably all of them. The easy part is break all the bonds that are part of the reactants, and then form all the bonds that you find in the products. But remember, I told you that you can use bond energies, and bond energies can only be used for gaseous. They're only defined for gaseous molecules. So there's a limitation that we have. So I'm just going to do a couple of more questions. Most of the questions are very easy. So for example, in this reaction, what they're looking for is they're looking for seeing what is the order of enthalpy changes of these reactions from most negative to most positive. So in the first one, I'm going to try and figure out this reaction number P, this P, its enthalpy change. I'm going to try and figure that out. So enthalpy change would be bonds broken. That would be endothermic. So in this reaction, only bonds are being broken. The only thing that's happening is you're breaking a Br bond, which is over here. That is 193. So that's it. And bonds broken. And bond formation, nothing is getting formed. So that is 0. So it's going to be plus 193. That's it. Next one, Q. You've got your a bond is being formed only. So broken, no bond is broken. So nothing is happening there. Formed, there's one ClCl bond that's formed, and the value is given over here. That is 190. The ClCl, that's 244. So that one is minus 244. Then you've got this reaction. Now, in R, how many bonds are broken? I told you to break all the bonds in the reactant. So there are 3 CH bonds that need to be broken. So these, I'm talking about R over here. So you've got these 3 CH bonds that need to be broken. And how many bonds need to be formed? It's CH3Cl. Like, you should know what the structure is. CH3. CH3Cl looks like this. So that means you're forming. So the bonds formed are 3 CH bonds, and there's going to be one CCl bond. And bond formation is all exothermic. That would be positive. So CH bonds would cancel out. I mean, they're going to get canceled out. So it's basically one CCl bond that's getting formed. I mean, you could have spotted that the only thing that's happening over here is that the CH3 bonds, overall, nothing is happening to them. The carbon is just adding another Cl to it. So that's one CCl bond that's being formed. So which is why it's going to be exothermic. And the value for that is minus 340. So the enthalpy change is you're not breaking any bonds. The only thing is you're forming a bond of CCl. That's minus 340. Up here, last one. The last one is you're breaking a CH bond. That's what you're doing. So the enthalpy change is you're just breaking a CH bond. That value is plus 410. So anyways, you've got these values and you just have to arrange them in the guide.
Sir, can you explain R again? Can you explain R again?
So R is this thing. It's CH3 plus Cl, and it's forming this thing, right? I mean, this is what R is, CH3.
Yes.
So how many bonds are broken? It's the bonds that are broken, I told you that break all the bonds in the reaction. So it's these 3 C and H bonds. They need to be broken. So 3 CH bonds that are broken, right? And bond breaking is endothermic, so that is positive. And how many bonds are getting formed? Form all the bonds that are present in the products. So it's 3 CH bonds and there's 1 CCl bond. So 3 CH bonds and there is 1 CCl bond. Now bond formation is exothermic, so the sign is going to be negative. So the enthalpy change is going to be the sum of all of this. Bonds broken and bond formation is all in negative because that's exothermic. तो क्या होगा? It's what's going to happen is that the CH would get cancelled out, right? I mean, even if you add them up,
Okay.
so you're just left with minus CCl, right?
Okay.
And that's minus
I
C.
understand.
Achha, next is you just have to arrange them in the right order from the most negative. The most negative is, I think, R. So it's going to be C. And the most positive out of this is S. So, I mean, just by looking at the first and the last value, you can figure out that the answer is C. Let's try and do one difficult question. There was one difficult question. Most of the questions are kind of easy. Like if you do this reaction, what's happening here? That there's an X2H6 molecule, and so there's 2X plus 6H. Now the reactants don't have any bonds. Like the 2X. Remember, when you have a coefficient, I mean, it's not a formula. It's so that means I mean, you just have 2X atoms. They're not forming any bonds. You got 6 hydrogen atoms. They're not forming any bonds. And you've got an X2H6 molecule. So the only thing that we can think of, I mean, you need to think what the structure looks like. So X is a non-metal. So it's probably something like ethane, where 1X would be bonded to. I mean, that's the only structure that we know of that even looks like X2H6. And he already told us that it's a non-metal, so it's probably a carbon atom, C2H6. So I mean, that's a best guess. So how many bonds are broken? No bonds are broken. So bonds broken, that is 0. How many bonds are formed? So X, between the X and the H atom, that's I mean, you can count that. Be careful. It's 1, 2, 3, and 1, 2, 3 over here. So that's 6 XH bonds. And there is one X and X bond that's also getting formed. And the overall enthalpy change, these values are going to be negative. They'll be exothermic. So the overall enthalpy change is already given to you. It's they've told us the overall enthalpy change. So it's minus 2, 7, 7, 5 is equal to bonds broken. That's 0 minus the bonds formed. So XH bond energy is given. So it's minus 6 times 395. And the other one is minus X, 1 into XX. So the XX bond energy is not known. So all you have to do is you have to find the XX bond energy. So I'm just going to rearrange the terms, bring the X and X on the left side. So it's going to be minus 6 times 395 and minus 2, 7, 7, 5. This would be actually plus. So can anyone tell me what the value is for this? And which one is the correct option in this case? And is this clear? Bonds broken, 0. Bonds formed, this.
Sir, it's A.
So it's coming out to be A.
No, it's B. It's B.
So I mean, you have to be, remember, you have to be very careful about the signs. It's very easy to get the calculation part wrong. So be very careful when you're dealing with the calculation. I mean, the rest of the thing is kind of easy, but I mean, people make a lot of mistakes when they're doing energetics questions. So just 1 second. So now the next, so I wanted to do a difficult question. I mean, this question is kind of easy as well. You just have to figure out the bonds broken and the bonds formed. So you'll be able to find the enthalpy change in this case as well. Same is, I mean, you can figure out this one, like how many bonds are broken? It's 2 NF3 molecules. So that means in an NF3 molecule, you will have, I mean, there are 2 of them. So that means a total of 6 NF bonds need to be broken. So that is the endothermic part. And how many bonds are formed? They're just atoms. No bonds are formed. So no bonds are formed, that's 0. So everything should add up to be equal to 1668. And they were looking for the NF bond energy. So only thing you have to do is get the 6 to the other side and you'll get your value. So it's going to be 1668 divided by 6, which would probably come out to be something around, my guess is 278, but you can just confirm. Like 1800 divided by 6 is around 300. This would be less than 300. So it's going to come out to be 278. Okay, is this clear? All these questions, is this all of this, is this clear? So is this clear? Amna, Alicia, is this clear? Mahad?
Yes.
So now let's try and see. I mean, most of the questions are going to be easy. They're not going to. So we did this. We skipped this one. So let's move to a slightly more complicated question, which is this one. Now in this question, and what I'll do is I'll just copy paste this one just a second. To get a difficult question. So I'll just put it on the board. Just a second, let it. Just hold on 1 second. So this one. So I just post it here. The difficult question. Now this one is he's asking a question, but everything is in terms of X and Y and N. So there's so people can get very easily confused with this. So what the question states over here is it states that which process just 1 second. So just hold on 1 second. The board has stopped working. Just give me 1 second. I'm back. So what it states is that we have to read the question properly. What it states is that which process could be used to calculate the bond energy. So he's saying you have to calculate the bond energy for the covalent bond XY. So this is what you're trying to do. You have to calculate the bond energy of XY by doing what? By dividing delta H by N. So the bond energy of XY must be equal to delta H, and that delta H must be divided by N. That's the question. So that's the first thing. You have to calculate the bond energy of the covalent bond XY by dividing delta H by N. So we need to find out who's going to give us that expression. So I'm going to look at option number 1 first. So if I look at the first option over here, which is A, what you'll notice is, if I write it over here, what you'll notice is that there's XY, N, and it changes into X gaseous atoms plus NY gaseous atoms. So the way you calculate enthalpy change is the same. Bonds broken minus minus bonds formed. Now the problem is, how many bonds are broken? Okay, that's the question. And how many bonds are formed in this reaction? So I'll just quickly give you an example. Like what I can do is I can think of X and Y. I can think of an equation which is very similar to this. Let's think of CH4. You got a CH4 gaseous atom. It breaks down and produces a carbon gaseous atom and 4 hydrogen gaseous atoms. So the two reactions are very similar, but the only thing is the previous reaction is in terms of X and Y, which kind of makes it confusing. This reaction over here is in terms of an actual reaction where you have CH4. So can anyone tell me how many bonds would you break in the CH4 molecule in this reaction? कितने होंगे? Like you have a CH4 molecule, so how many bonds would be broken over here? Is there any idea, Oswa?
4.
Okay, so it's obviously 4. So you're going to break 4 CH bonds, and they would be broken, so that would be plus. And how many bonds are you actually forming? You're not forming any bonds, right? Because they're just atoms. They're not forming any compounds, they're not forming any molecules. So it's just 4 hydrogen atoms and 1 carbon atom. So no bonds are actually formed. So we can do another reaction, which could be very similar to this one. So let's do another example. I've got a PCl5 molecule, and it's gaseous. There's a reaction, it breaks down, I get a phosphorus gaseous atom, and I get 5 Cl gaseous atoms. Same thing. How many bonds will I be breaking over here in this molecule? It's going to be 5 PCl bonds, right? Because it's a PCl5 molecule. So basically that means it's 1 phosphorus with attached to 5 Cl atoms, right? It's attached to 5 Cl atoms. So I would be breaking 5 of the PCl bonds. And this is 5 actually. And how many bonds am I forming? I'm not forming any bonds. They're all just atoms. So no bonds are formed. So in this case, no bonds are formed. So what I'm going to do is I'm now going to move to the equation, which is in terms of X and Y. I'm just going to compare them with the reactions that I just did. So if you have CH4, how many bonds you're breaking? You're breaking 4 CH bonds. If you have PCl5, how many bonds are you breaking? You're breaking 5 PCl bonds. So if you have X, Y, N, so how many bonds are between X and Y? That's N bonds of X and Y. These are the ones that are broken. You can remember the 4 over here, that's 4 CH bonds. 5 over here, that's 5 PCl bonds. If there's an N over here, that would be N bonds of X and Y. Is this clear? Yes or no? Is this clear?
Yes.
Okay, Baki clear. Read, is this clear? Mahad? Just a second.
Yes, sir.
Achha, so, and how many bonds are you forming? You're not forming any bonds. You just have atoms over here. So bonds formed, that's exactly 0. So that means your enthalpy change. What is your enthalpy change equal to? Your enthalpy change is basically equal to, your delta H would be equal to plus N bonds of XY and no bonds formed. Okay, so that's, and if I rearrange this, what's going to happen? If I rearrange this, what's going to happen is that, just a second, let me move this. So if I rearrange this, the XY bond energy, if I rearrange this, the XY bond energy is basically equal to delta H divided by N. Okay, that's equal to delta H divided by N. And this is exactly what he was looking for. In the question, he had specifically asked for, can किसकी bond energy is for the covalent bond XY can be found by dividing delta H by N, and we got the right expression. So is this point clear?
Yes.
Okay, so that's going to be our answer because this is what he was looking for. But just for the sake of like practicing this even more, I'm going to try and do part B. I know B is wrong, okay, but we're going to try and do part B. So let's copy part B. Just for the sake of figuring out how many bonds are we breaking and how many bonds are we forming. So it's 2 molecules of XYN gaseous, and there's X, which is gaseous. This is part B, and there is sorry, it's not X. It's actually 2XY, and there is N minus 1. And then you've got a Y2, which is gaseous. Forget the state symbols, all of them are gaseous, so you have to use bond energies. Now look at this reaction. Let's try and figure out how many bonds are broken. So remember this, what we just did. XYN, that means you're breaking N bonds of XN. You're breaking N bonds of X and Y. But I mean XYN, that means like CH4, you're breaking 4 CH bonds. Like PCl5, you're breaking 5 PCl bonds. And there are 2 molecules. So that would be multiplied by 2. So these are the bonds that are broken. Is this clear? This thing?
Yes.
So then similarly over here, X, Y, N minus 1. So again, it's like, I mean, whatever N minus 1 is probably a whole number. But it's like, again, it's the same as CH4 or PCl5. So X, Y, N minus 1. So that means you're breaking N minus 1 bonds of between X and Y. Right? If this was CH and 4, that would be 4 CH bonds, right? So whatever N minus 1 is, you're breaking that many bonds. And there are 2 molecules, so you're going to multiply that by 2 as well. And over here, it's a Y2 molecule, so that's a Y and Y bond that is also getting formed. So these are your bonds that are, let's ignore this. These are the bonds that are formed. And bonds broken is endothermic. That would be positive. And bond formed would be exothermic, so they would all be negative. And your enthalpy change of the reaction is going to be equal to this entire thing. So in terms of X and Y, I was able to figure out how many bonds are broken and how many bonds are formed. But anyways, in this case, I'm never going to get the expression which they were looking for. And the same, we can try this one, like how many bonds are broken? So this is an atom, you're not breaking any bonds. So XY, so N minus 1 bonds of XY. So I'm just going to write it over here. So how many bonds broken? N minus 1 bonds of between X and Y. These are broken. And that would be endothermic. How many bonds are actually formed? It's N bonds of X and Y. Sorry. It's N bonds of X and Y that are formed, right? So N minus 1 bonds of X and Y are broken and N bonds of X and Y are formed. Plus this is just an atom, so no bonds are being broken over here. So the enthalpy change would be, this is positive, this is negative. So the enthalpy change is going to be the sum of all of this. Is this clear? This one? Is this clear? Yes or no? So, and if you have,
मतलब इस सब के बाद क्या बनेगा enthalpy change, मतलब इसको simplify
if I try to simplify this, okay, so this could be further simplified. It could be simplified like it's going to be N into XY bonds, right? So it's going to be n into xy bonds of a -1 into xy bonds. But n -1, right? And then it's minus n times xy bonds. I'm simplifying this. And that's equal to delta H. Now, if I simplify this, so what will happen is this n into xy bonds minus n into xy bonds, that's going to cancel out. So delta H would be equal to the negative of the xy. So it's going to be equal to this. So he might have given, I mean, he could have given you this question as well. Like he could have asked you that the bond energy of xy is delta H divided by -1. I mean, it is delta H divided by -1. Like if I just bring the -1 to the other side, like if I make this plus or simply this one, that the xy bond energy is basically equal to the negative of delta H. So is this clear?
Yes.
So we're just practicing the other ones because you should be able to do this because you could have asked about any one of the equations. And similarly over here as well, like how many bonds are broken? That's how many, this one, how many bonds are broken over here? So how many bonds do you have? It's xy. Up here, there's one, obviously. There's no number over here. So that's just xy. So there's just going to be a bond between x and y, but there are n molecules. So if I do this over here, it's going to be, you're just breaking an xy bond, but you're breaking n of them. So that's plus. And then how many bonds are formed? So that's just an atom. TK not bonded to anything, so you're not forming any bonds. So that's 0. That's a molecule, Y2 molecule. So you're forming a YY bond. And how many molecules are you forming? You're forming n/2 molecules. So that would be because you're forming it, so that's going to be exothermic as well. So your delta H would be equal to all of this. It's going to be bonds broken. So you're breaking XY bonds, but they're n molecules. So you're breaking n number of XY bonds. Bonds formed, that's 0. It's just an atom. Over here, you have a Y2 molecule, so you're forming a YY bond, and there are n/2 of them. So that will give you this expression. So is this question clear? Clear, Saroko?
Yes.
Okay, so let's now discuss just one more thing, which is, so this is probably the toughest question that you can get. I mean, if they want to, most of the questions are going to be kind of straightforward. All you have to do is you have to be careful with the calculation. So I said, let's do one more thing, and that is that bond strength. Let's talk about bond energy values. So we'll just quickly talk about bond strength. Now, remember, when you're talking about bond energy, it's energy. We did discuss the definition. So remember this. If you have a stronger bond, it would be more difficult to break a stronger bond. If you have a stronger bond, more energy needed to break it. So that means it will have obviously a higher bond energy. So it's pretty obvious. So how do you figure out which bond is stronger? Like if you had to guess which bonds are stronger, the first thing is you've got 3 types of bonds. One is a single bond. Then you've got a double bond between atoms. And then you've got a triple bond that exists between atoms, right? So the first thing you should know is that when you, like, a triple bond is stronger. That's obviously stronger. And a single bond is obviously, it's obviously going to be weaker. That's the first thing. I mean, you can look at the bond energy data. If I open the data booklet, just type 9701 data booklet. You'll get this data booklet. So if you look at the bond energy table, which is right at the beginning over here, you will be able to see that single bonds, they have less energy. All of a sudden, you got a triple bond, that's 944. Even double bonds are kind of strong. That's 496. That's on the higher side. Even carbon monoxide, that's a triple bond. That's really hard to break. So that's the first thing. Single bonds are weaker. Triple bonds are stronger, kind of obvious. The other thing is, you should also remember, there's another factor, and that factor is that when you have smaller atoms usually make stronger bonds. They make stronger bonds, and the reason for that is that that when you have smaller atoms, they're closer to each other. There's going to be more attraction. But as a rule of thumb, remember this, and this always happens. Like no matter what type of bond this is, whether it's ionic or I mean, remember over here we're basically talking about molecules. We're talking about covalent molecules. Bigger atoms are further away from each other, which is why they always form weaker bonds. So as a rule of thumb, smaller atoms, they always make stronger bonds. Bigger atoms make weaker bonds because bigger atoms are further away from each other. So there would be some questions where they would ask you to predict the bond energy. So for example, they might ask you that you've got these hydrogen halides. So we're moving down the group. So the atom is kind of becoming bigger and bigger. So this is obviously going to be it's going to be weaker. It's going to form weaker bonds. And the smaller the atom, the stronger would be the bond. So for example, what we can do is we can have a look at the bond energy table as well. Like you've got HI, HBr. HI is going to be the weakest. So if you look over here, you'll see that you have HI. It's the weakest. HBr is stronger. Smaller the atom, the stronger the bond. HF is one of the strongest. So just make sure that sometimes they'll ask you to guess bond energies. So based on this, you should be able to guess bond energies. Is that clear?
Sir, what if HI had a double or triple bond? Then which one would be?
फिर confusion हो जाती, ठीक है? I mean, you can't remember. It's not. It's just. I mean, there are two factors involved, right? So the thing is, you'll be able to guess sometimes, but not always.
Okay, but like they won't give us mixed questions like where they are weaker and stronger bonds and the atom size.
You wouldn't be able to predict it. Like you wouldn't really. I mean, it would be impossible to predict. Then you would have to actually check the value. Okay.
Okay.
I mean, for example, in this worksheet, there's a question somewhere which was talking about bond energy. It's this one. He was saying which one is the strongest bonds, right? So if you look at the data booklet, you can just open the data booklet. A is CNH bond. So CNH is given over here. So CNH is given over here. That's 410. So I know this is 410. Actually, B is C and C bond. So if you look at the C and C bond, that's over here. That's 350. So I know that B is 350. And then I had the CF and CCl bond. So if I look at the data booklet, I'll see a CCl bond that's 340. So I've got 340. And the last one is the CF bond. Remember, we're looking for the lowest bond energy. So if you look at the CF bond energy, there is, I mean, they didn't give, I mean, that isn't even part of the data booklet. So now your prediction part will come in, because even if you look at the data booklet, you've got CI, you've got CBR, you've got CCL, but there is no CF. So the question is, what would be the approximate value for this one? Now, I can't compare this one with the CC and CH bond, but what I can do is I can compare it with the CCL. So which one would be stronger? Is it going to be CF or is it going to be CCL? Which one is the smaller atom? What's the answer? Any guesses? Like, who's going to have a stronger bond between the two?
CF.
It's going to be CF because remember, it's a smaller atom. So it's going to be CF, and so that means it's going to be stronger, which means its bond energy would be higher. So I'll just make up one bond energy, like it's going to be greater than 340. So let's say it's 360. I mean, this one is just a made up value. So he was looking for the lowest bond energy. So that is by default, out of all of them, is going to be CCL. So the answer to this question would be, it's going to be D. Why? Because out of the three, the lowest was CCL. The only problem was I didn't have the CF bond energy, but I was able to figure out that it's a smaller atom, which is why it's going to be stronger, which is why it would be more difficult to break. So its bond energy would be higher. So if it's higher than 340, that means 340 is the one that's lowest, right? So hopefully this question is also clear. So we're kind of done with bond energies. Just make sure that whenever you deal with bond energies, you're going to look for two things. It's either all the substances are in gaseous state, then you use bond energies, or they explicitly ask you to use bond energies. For example, in these questions, I mean, most of the time, all the substances would be in, I mean, they'll give them in gaseous state. Sometimes they'll not, I mean, all of them are gaseous, right? Sometimes, like if I can see a question, sometimes they wouldn't mention the state, like over here, they're not mentioning the state. But they have, I mean, they're explicitly asking you to use bond energies, so you can then use bond energies. So that's it. Now, the other thing that we're going to talk about is the energy profile diagram now. And we're going to talk about the activation energy. So activation energy and the energy profile diagram that you've studied in O levels. So that's related to, because every reaction you have bonds being broken and bonds being formed. So I'm going to draw the energy profile diagram for So I'm going to draw the energy profile diagram of an exothermic reaction. So let's focus on an exothermic reaction. Most of you in O levels, you must have done this. In an exothermic reaction, your reactants are at a higher energy and the products are at a lower energy. And the curve is something like this. So it goes, this is your energy axis. And that is the progress of your reaction, or the time taken for the reaction. This over here is your, I mean, these are your reactants. And these over here are your, I mean, they're your products. And the enthalpy change, remember, is the net energy change. So it always starts from the reactants to the products. So that is your delta H. So that's the net energy change. In an exothermic reaction, you're losing energy. So the products are always at a lower energy because they've lost energy. And then you've got this activation energy, which is, it starts from the bottom and reaches all the way to the top. That over here is your activation energy. Now, the thing is, why is the curve like this? The curve is like this because the first part is endothermic. I mean, the very first part, this part is endothermic. It's endothermic. Why is it endothermic? Because the first part is you're going to break bonds. And then new bonds are formed. So that part is exothermic because bonds are getting formed. So which is why every reaction needs energy at the start. They gain energy and then they release energy. Like if you're burning paper, you heat it up and then it burns and it produces energy. So why is energy needed? Because it's pretty hard to break the old bonds. You want to make the molecules energetic. Like if you're burning wood, why do you heat it? You heat it ताकि जो oxygen के molecules हैं, they have enough energy that when they collide with the molecules in the wood, they break the bonds. Why do you strike a match? The reason you strike a match is that you want the molecules to hit each other with enough force that the old bonds are broken. That's activation energy. That's why energy is needed at the start of the reaction. The bonds are not going to break on their own. So when you're lighting up a match, the reason you strike it with such force is you want them to collide with enough force so that the old bonds get broken. Once they're broken, then new bonds are possible. New bonds would be formed. And that part is bond formation is exothermic, which we did over here. So which is why this is the energy profile diagram of an exothermic reaction. Bonds are broken and then bonds are getting formed. So I'm going to explain why this reaction is exothermic. The reason this reaction is exothermic is, in O levels, you used to get this question, why is this reaction exothermic? The reason this reaction overall is exothermic is because less energy is taken in to break old bonds. Which kind of indicates that the old bonds might be really weak. So, like if you strike a match, the old bonds get broken very easily. So less energy is taken in to break old bonds. So you've got these weak old bonds which are easily broken. And more energy is released, relatively speaking, and more energy is released when new bonds are formed. Which kind of indicates that that the new bonds formed are stronger. So which is why the overall reaction is exothermic, because ऊपर कम जा रहा है, less energy is taken in to break the bonds and more energy is being released to form new bonds. So which is why the overall reaction is exothermic. But every reaction is going to have activation energy. You would need to give them energy so that the old bonds get broken. You strike a match with force so that the old bonds are broken. If you want to burn a piece of paper, you heat the paper. The reason you heat the paper is that the air molecules and the paper molecules, they bump into each other with enough force that the old bonds get broken. So that's exothermic. So we're going to do endothermic tomorrow, which is kind of, you already did that in O levels. We're going to do the effect of catalyst as well on the speed of the reaction. So we'll just cover this quickly. That's most of this is O level stuff. Okay, we'll just do a quick revision. So is this clear? Yes or no? Is this clear?
Yes.
ठीक है, चलो ठीक है, let's continue tomorrow then. Okay, everyone.
Allah Hafiz.
Take care. Allah Hafiz. Allah Hafiz.